Yeah. Welcome to 10th week of our Electrical Machines 1 NPTEL course. Since the last 9 weeks we have discussed several topics on transformers. We started with transformers and we discussed many topics on transformers, and since 8th week we started discussing our DC machines concepts, and inside the DC machines we discussed winding, how the winding of a DC machine is done, and then armature winding, field winding, lap winding, wave winding, such concepts we discussed, and we started discussing EMF equation of a DC motor, and also torque developed inside the DC motor we discussed. And today we are going to see a few basic concepts in a DC shunt motor, and we already derived some equations on DC shunt motor last week, and even the week before we derived EMF induced equation in a DC motor as well as torque developed in a DC motor. So we will be using those two equations again. I'll be writing those equations again for your reference, and then we will start discussing a few numericals on DC shunt motor. So with that, I'll start discussing today's session, and yeah, just for refreshing our concepts of EMF induced in a DC machine and as well as the torque developed in a DC machine, I'm just writing the equations we derived last. One second, someone has joined. Yeah. Just to brush up the concepts, I will be writing the EMF induced equation which we derived 2 weeks back, and also the torque developed in a DC motor or a machine we derived 2 weeks back again for you here, and so that we will be using those equations again for today's numericals. So let me start. EMF induced equation I am writing. Okay, one second. E is a proportionality. EMF induced is proportional to phi, that is flux developed in a field winding, and also speed with which the machine is rotating. So the constant part, which is Pz by A. So we know that what Pz by A stands for. P is number of poles in the machine, and Z is the number of conductors, and A is the number of parallel paths, and multiplied by phi, that is flux, and also N. N is nothing but the speed at which the machine is rotating. So this is EMF generated equation, and the torque developed equation is K phi Ia, where the constant K is Pz by 2 pi multiplied by phi, that is flux generated. Again, it's also proportional to the flux generated by the field winding, but multiplied by, this is not dependent on speed, but it is dependent on the amount of current flowing through the armature winding. So these two are the basic and fundamental equations for any kind of DC machine. So if you are doing any kind of DC machine, whether it's a series connected machine, shunt connected machine, compound machine, compound series, compound shunt, or a separately excited DC machine, any kind of DC machine, these two equations will valid for any machine or for any kind of problem you are going to solve. So these two equations are very basic equations and very important equations for the DC machines. So how we got these equations, why we got Pz by as a constant, how it is proportional to phi and speed for EMF, and how it is proportional to phi and armature current in a for the torque developed. We derived those equations 2 weeks back. You can just go through that lecture as well, go through that session. That video is available in the YouTube, so you can clearly understand why a torque developed is proportional to phi and Ia, and why EMF induced is proportional to phi and speed. Yeah, I hope you recall these two equations of EMF induced and torque. And today we will be discussing basic concepts in a DC shunt motor. So we already know in a DC shunt motor, the armature of the motor will be there, and in the shunt of that machine we will connect a field winding. So the field winding will be in shunt position, or we can also call it as a parallel position. So if we connect field winding in a shunt position, we call a DC shunt motor. If it is in series to the armature winding, we will call it a DC series motor. So in a shunt motor, motor armature and motor field winding will be parallel to each other, across which we will be giving the input supply. So the same input voltage will appear across both armature winding and shunt winding as well. So let's look at that kind of connection again in terms of picture. So I'm just, so this is the field winding, and this is armature brushes A1 and A2. I'm just drawing, and yeah, this is the brushes. Yeah, and inside the armature winding we know there is a armature resistance RA and also the back EMF EB. Armature resistance, this is EB, let's represent it RA, and plus minus it will be EB. And yeah, across these terminals what we will be giving? The supply. This is, we call it here the voltage, 1 second. Yeah, here the voltage across the both armature and the field winding is same, and it is same as the input supply. So there is no separate voltage like armature voltage VA and total supply voltage V. Both the voltages are same. So input voltage V is same as VA, is same as VF, that is field winding. And yeah, this is RSH. Shunt, because SH stands for shunt, it is also the field winding. Okay, now yeah, let's say we want to add some resistance inside the armature. So if you see the RA here, that is the armature resistance came with the machine. Now I want to add an external resistance to that machine. So I place an extra resistance, that is say R external, in series with the armature. Then we say that we are adding a series resistance in series with the armature, such that we are increasing the total resistive component of the armature winding. We can do that because if we want to control the speed, so speed control of a DC motor can be achieved by adding this external resistance. And to see that, we will be solving some numericals, and yeah, so we'll be solving some numericals where we will calculate how the speed can be changed based on the armature winding. Let's say in the first case we have X ohms of armature resistance. In the second case, what we will be doing is we will be adding a small external resistance in series with it, and we will see how the speed of the DC machine is varying. Even for that, if we want to calculate the new speed for the armature with the added external resistance, what we will do? We will just find the EMF induced in an equation in the DC machine, and we know that the EMF induced is proportional to flux and speed. So that's the basic concept for any kind of DC machine. So yeah, someone switched on the mic. Can they unmute themselves? Okay. Okay, I did that. So let's go through this particular numerical we are seeing here. So we are provided with a 220 volts DC shunt motor, and for what purpose we are using this machine? We are using it to drive a load which is a constant torque. So this is very important. There are different kinds of loads for any application. It can be constant torque load, it can be constant power load, it can be, so when we come across such terms, you have to notice that, so whatever might be the current flowing through the load, it should always operate at a constant torque. Such kind of load is called a constant torque load. And when it comes to constant power load, whatever voltage, whatever current it is taking the load, but we need to make sure that the load should always be delivered only same power, because that load is destined to operate at a constant power load. So such loads we call CPLs, which is constant power loads, and CTLs are constant torque loads. So there is an added data we are provided with in the question. So it says that we are using our DC shunt motor to drive a load which is a constant torque load. Okay, we will keep that information aside. And what else were given in the question? So at no load, the motor takes 1 ampere of armature current and it runs at 1100 RPM. So again, the last week we have solved some basic problems on DC shunt motor, where we have calculated the induced EMF for no load condition first, and also some loaded condition given. So in the same manner, here we are provided with a no load condition first. It is saying that under no load condition, our armature is taking only 1 amp. We know under no load condition what is the condition for a DC shunt motor, any kind of motor. So if you are operating some kind of motor in a no load condition, it means that the only load present at the time is load is not there. So whatever power we needed to drive the machine is only to supply for the losses, that is nothing but rotational losses. So we already discussed thoroughly what rotational losses are actually, and what kind of losses contribute to rotational losses. So just to recall it again, I am telling you rotational losses are nothing but friction losses, windage losses, eddy current losses. So under no load condition, whatever power is generated in a motor, it is required to supply for these three kinds of rotational losses. So keeping that in mind, so at no load, our motor takes only 1 amp armature current, fine, and also it runs at 1100 rpm. Okay, so armature resistance is 0.5, that is constant even under load or no load. 0.5 armature resistance is constant. Now when the load is applied, so this is the second condition, when the load is applied, the motor takes 25 amps of armature current. Of course, when there is a load we have to drive to our motor, the motor needs to draw more amount of armature current from the supply. So it was given that 25 amps of armature current it will be drawn by the load, drawn by the motor to drive that particular load. Here comes the main part of the question. So they are saying that suppose a 3.5 ohms resistance is inserted in series with the armature.
Your screen is not visible.
Okay. My PPT is not visible?
Yes, sir.
Okay. Is it visible now?
Yes, sir.
Okay, thank you. Thank you for pointing it out. Yeah, thank you. So I was saying that it was given a separate condition in this question that we are adding an external resistance to the armature. That is nothing but 3.5 ohms of resistance. We are physically adding that resistance to the armature circuit in series. Now we have a new kind of motor which is nothing but a added resistance in the armature. Now in this condition, let's see what the question was about. So it's about when we add such kind of external resistance, we have to estimate the no load speed after connecting the 3.5 resistance. So we already talked about this in the starting of today's session, that to control the speed of a DC motor, one of the technique is the armature resistance control method. So you can change the armature resistance value and we can get variable speed across it. So here is one of the example. So when it is 0.5 ohms of armature resistance is there, my DC shunt motor is rotating at 1100 rpm under no load condition. So under the same no load condition, when my armature is added with 3.5 ohms resistance in series with it, now I want to see how much speed it is rotating now in the second case. That is the new speed of my DC shunt motor when I have added 3.5 ohms of resistance in series with the armature. So let's try to solve this question, and it's pretty, I will go while solving this question, I will go with only the basic equations which we started today's session with, that is EMF generated equation, that is basic for any kind of DC machine problem. Now before going to the equation, let's draw how a motor would look like with and without this kind of external resistance. Okay, let me draw it here. Okay, I have drawn the shunt motor. So this is the shunt field winding, and this is the DC machine armature. These are the brushes, output terminals of these pressures, and here I am having the supply. So what is the supply it was given? It is 220 volts DC shunt motor, and inside the armature I have the armature resistance and back EMF, RA and EB, and this is the RSH. So RA is, we know RA is 0.5 ohm, EB we don't know. Do we have the information about shunt resistance? No, we don't have, because shunt resistance is same in the both cases. We are not adding shunt resistance, but we are adding the armature resistance externally. Now, yeah, assume no load torque to be constant. See, no load torque to be constant. So it is saying that whatever torque that is required in the no load is only friction torque and windage torque and eddy current force that is developed. So all these torques are constant, so we don't have to bother about that torque as well. Okay, now what was the question? We have to estimate the no load speed in RPM after connecting the 3.5. So first calculate no load. There is again two kinds of conditions, right? No load condition, on load condition, and we have to calculate the no load speed, and also no load speed will. First what we will do is, for load and no load, for actual RA resistance, initially there is only 0.5 ohm resistance, right? At that 0.5 ohm resistance we will calculate how much amount of EMF is induced. So let's just put the data here, what information is given to us. So what is the armature current in no load condition? That is 1 amp, and no load speed is also given, that is 1100 RPM, and armature resistance is equals to 0.5 ohm. So coming to on load condition, my armature current is 25 amps and armature resistance is same for no load or no load, it's 0.5 ohm. Okay, now in these two conditions let's calculate the EMF induced in no load. So EB is the back EMF and NL is no load. That's the notation I am following. Now what is the equation for a DC shunt? One second, someone has joined. Yeah, so the equation for motor equation is EMF induced is equals to terminal voltage or the voltage across the armature. This is same because it's a shunt motor. V minus armature current into armature resistance. Now what is the voltage? We know it is 220 volts minus IA RA. So what is IA in this condition? 1 amp into 0.5. So how much is this? Someone also calculate along with me. 220 minus 0.5, that is 219.5 volts. So this is the back EMF that is induced in this motor under the no load condition. So for the same thing we will calculate the EB under loaded condition. This is only first case where only the armature resistance is 0.5. I have not gone to the external resistance added case. Let's see what we will get here. So EB under loaded condition, L, that's why it is L, and same thing, V minus IA RA. So here V is same, 220 minus IA 25 multiplied by RA. So 220 minus 12.5, how much it is? 207.5. So volts. EB under loaded condition. So this is EB under no load condition. Now okay, this is my actual for my given motor without any change in my armature resistance. These are the values of back EMFs under no load condition as well as the loaded condition. Now after adding external resistance, we will do the same. We will see how much is the EMF induced in both no load and loaded condition. Okay. Okay. Now after adding 3.5 ohms in armature winding. Now let's see. No load. Now what else will change? Current same. Now that is 1 amp. Now the new RA is 0.5 plus 3.5, that is 4 ohms. Here IA is 25 amps. Okay. Okay. Now same EB no load, but I'm just keeping a dash because it's the second condition where my armature resistance is 4 ohms here. 220 minus IA RA, it is 216 volts, and EB dash under loaded condition 220 minus 25 into 4, 100, 210 volts. Now so these are the new back EMF values after adding this series resistance in armature.
120 volts.
220 minus 100. Oh my god, yeah, thank you, it's 120. Thank you for pointing it out. Yeah, 120 volts, correct. Okay, now what was the question? We have to estimate the no load speed after connecting the 3.5 ohms. So see, EB no load we know, EB dash no load we know, omega under no load, that is speed in no load we know, and what we were asked, omega dash NL. Omega dash is nothing but this, no load speed after connecting 3.5, right? Now what is this? How can we find this? We know the basic equation. What is the equation? EB is equals to PZ by A multiplied by phi multiplied by N. So this N is in radians per second. So EB is proportional to 5 and phi and N. So this is anyway constant. So yeah, EB1 by EB2 is a proportionality. That's why I'm writing it like this. Phi 1 into N1 by phi 2 into N2. Now if you see here, phi 1 and phi 2 is nothing but the flux generated in the field winding before and after connecting the resistance. Now one thing we observed is, whatever might be the armature resistance, even if you add some resistance, even if you reduce the resistance, my field winding resistance is not at all changing. My RSH is same, the current received by then the voltage supplied is same, so the current drawn by the field winding is always same no matter what the armature resistance is. It is independent of that. Now we can say that from that relation, phi 1 and phi 2 is also constant. So phi 1 and phi 2 are same. Now with that, what we got, EB1 by EB2 is equals to N1 by N2. So let's say EB1 is our no load speed at 0.5 ohm armature resistance. What EB2 is back EMF, no load EMF under when I added 3.5 R series resistance, and N1 is a speed at no load condition when my armature resistance is 0.5. N2 is what required. N2 is nothing but the no load speed after connecting the 3.5 ohm resistance. Now from this relation we can easily calculate N2, that is N2 is equals to N1 multiplied by EB2 divided by EB1. So what is N1? N1 is nothing but this one, no load speed under no load condition. 1100 multiplied by EB2 after connecting 3.5. What is the value we got? After connecting no load, it is 216 volts. 216 divided by before connecting, how much we got? 219.5. So someone calculate this for me. I will also calculate. (216 by 219.5). Anyone calculated? So my new speed is 1082.46 RPM. So you can now see initially my yes
EB2 divided by EB1 है ना?
yeah EB2 is the voltage after adding series resistance. All the twos are secondary, like that is the second case where I have added 3.5 resistance. Okay, I'll just write it like this. 1 second. It could be of a confusion. Let me write again like this. EB no load by EB dash no load is equals to N no load by N dash no load. Okay, now what it was required is N dash no load. Now from this equation, what is N dash no load? N dash no load is equals to N no load multiplied by EB dash no load divided by EB no load. You can see N no load is 1100, EB dash no load, that is this one, the corner one, 216 volts, divided by EB no load, that is the first no load EMF induced, 219.5. After adding 3.5, we are getting 216. Got it? You understood now? Okay. So I hope you got this speed as well, 1082.46. Now what you have observed here is, initially my armature was resistance is 0.5 ohms only. Now my armature resistance is 4 ohms. So as I increased my resistance, my speed dropped. You can see that initially my no load speed is 1100 RPM. Now the armature, my motor is running at 1082.46 RPM. So my speed has reduced when I increase the armature. That's obvious. When you increase the resistance and the drop would be more, my speed will be less. So yeah, that's how you calculate the no load speed. We again use the same basic equation here. My EB is equals to PZ by A multiplied by 5 multiplied by N. So yeah, from that relation only we got how what it would be the new speed whenever I change my armature resistance. Okay. Now, so we have to estimate the. Now the second question is, we have to estimate the on-load speed. So now we don't have to deal with no load parameters. Now we have to deal with the loaded condition. In the in the loaded condition, we have to calculate the speed. So I hope you know how to do it. You also try to solve it with me, and yeah. Loaded condition, we already calculated everything, no? Yeah, we know 120 volts is the loaded condition, and loaded condition is 207.5. Okay, I will just write it here. EBL, this is when my armature is 0.5. How much is EBL? 207.5. 207.5 volts. Do I know the load speed in this? N load? No, I don't know. It was not given. I was given only no load speed. Now EB dash L is 120 volts. 120 volts. And N dash L is the question asked. Okay. What else I know? EB no load. How much is EB no load? 219.5. 219.5. So what is NNL here? That is given in the question, 1100 RPM. And what else I know? EB dash NL. How much is EB dash NL? That is after adding 3.5, it is 216 volts. And what is the speed at this condition? N dash NL. 1082.46. 1082.46 RPM. Now I need to find this particular question, and it is again a very simple question. So if I know this speed, I could have do the same proportionality constant with it. I don't know this. So but you know both EMF and speed in these two conditions. So use any of the condition you can easily get. Again I am writing EB is proportional to 5 and N. Now EB1 by EB2 is equals to phi. It's again field current is same in both conditions. N1 by N2, right? Okay. Now what else this one should be known, and this one should be known. This is the thing it was asked. So first condition I can take either no load this one or no load this condition, anything you can take. So I am taking EB no load. So what was asked? This one. So this speed is asked. So the EMF proportional to this is EB dash loaded is equals to N at no load by N dash at loaded. So this we don't know. This we know. This we know. This we know. So can someone please tell me how much is the on load speed after connecting 3.5? It is nothing but no load speed before connecting 3.5 multiplied by EB dash, that is on load EMF after connecting 3.5 divided by no load EMF before connecting 3.5. So what are these values? What is NNL? It is 1100 multiplied by EB dash L. How much is EB dash L? 120 divided by EBNL. How much is EBNL? 219.5. Can someone calculate this? 1100 multiplied by 120, 219.5. I hope you also got the same. 601.366 RPM. You got the same?
Yes, sir.
Okay, great. So this is the on-load speed in RPM after connecting 3.5 resistance. So these kind of problems they will frequently ask. I have added the resistance. Someone came? Okay, these kind of problems I will frequently ask. I have added the resistance, I have removed the resistance, I have increased the speed, I have decreased the speed. So in all these conditions, if you want to find, either you have to find EMF induced or you have to find the speed. So go with the basic equations we know. EB is proportional to phi and N. You keep in mind, are you changing the field resistance in the question? If the field winding is also changing, let's say they have increased the shunt resistance from both cases, then the flux generated will also change. It will definitely change because that flux is nothing but the field generated in the field winding. Once my field resistance changes for the same terminal voltage, the current drawn by the field winding will definitely change. So you read the question carefully and you note down the conditions. What are all the parameters they are changing? Are they changing only armature resistance? Are they also changing the field resistance? And you note down, and based on that you apply this proportionality relation. It will be very simple. So but you have to be careful with the calculations. Okay, now yeah, the answer for this question is the on-load speed after connecting 3.5 ohm resistance is 601.366 rpm. Okay, yeah, I hope this question is also clear. So let's see the last sub question for today. It was asking estimate the speed regulation in percent of the no load speed after connecting 3.5. Now when the speed regulation, what is regulation? Regulation means, let's say you are having some x value now. In another condition you are having y value. So how much speed has been regulated? It is nothing but x minus y. So that's the difference in whatever quantity you are seeing. If it's a speed, first it is x rpm, in second case it is y rpm. The speed regulation is x minus y. So it can be in terms of percentage also. When it is asked in terms of percentages, you will take the subtraction of it, x minus y, divided by what speed, in terms of what speed percentage you want. If you want in percentage of percentages of x only, initial speed, x minus y divided by x multiplied by 100. That is nothing but percentage regulation. Now in this question, if you read the question, it was asked we have to estimate the speed regulation in percentage of the no load speed. So we have to see how my no load speeds are varying in both cases before and after connecting the 3.5 resistance. So see, okay, only after connecting 3.5 resistance only we are seeing, but the percentage should be no load. So let's write a comprehensive values here. After connecting 3.5 ohm resistance, what are my values? After connecting means all will be EB dash only. EB dash NL, EB dash L, and that is the EMFs for loaded and no load, and this is speed. Okay, we are writing it N. Na? Let's follow the same convention. N dash NL and N NL. Now what is EB dash NL? EB dash NL is 216 volts. EB dash L, my EB dash L is how much? 120 volts. Now in my no load, what is my speed after adding N dash NL? 1082.46. 1082.46 rpm. And what is my no load speed? Okay, this should be loaded. Huh? Okay. N dash L. What is my on load speed after adding 3.5? N dash L, that's what we calculated here. 601.366. 601.366 rpm. So these are the values after adding 3.5, all the values. So now see what he's asking. Speed regulation. Okay, the regulation between these two speeds as a percentage of no load speed. As a percentage of no load speed. It's simple. So percentage speed regulation is equals to no load speed minus on load speed divided by, the denominator will be decided by this question only. He asked in terms of no load speed. Again no load speed multiplied by 100. This is N, speed, and this is also speed. So what is the no load speed here? 1082.46 rpm minus 601.366 rpm divided by, what is the speed again, no load, same, 1082.46. So multiplied by 100. Okay, someone calculate it with me and tell me how much you are getting. 1082.46 minus 601.366 divided by 1082.46 into 100. So how much you got? You also got the same 44.4. Anyone get the same answer?
Yes, sir.
Okay, good. So it means that my speed variation is very high here. From 1000 rpm to 600 rpm, it's almost 40% variation I have observed when I just like after connecting 3.5, my speeds between no load and load has been changed around 44%. So this speed regulation is very high. It's not desired actually, this kind of speed regulation. And yeah, this is the way to calculate the speed regulation. Regulation of speed means whatever conditions he's asking, you take that condition, you take the difference, and to get in terms of percentage, you divided it what parameter you need in terms of percentage. Here in the question it was asked in terms percentage of no load speed. That's why my denominator is 1082. If it was asked in percentage of on load speed, then the denominator would be 601.366. Okay, so this is the few concepts we have discussed today. And yeah, so just as a revision of today's discussion, we started with discussing basic fundamental equations in a DC machine. That is, my EMF induced is equals to Pz by A multiplied by phi multiplied by N, where Pz by A is P is number of poles, Z is number of conductors, A is number of path. This will be always be constant once you fix the machine, because once I fix the machine, number of poles are constant, number of conductors are constant because winding is constant, and number of parallel paths are constant. So the variable quantities will be the flux generated and also the speed at which my motor will rotate. So coming to the torque equation, it's the equation is Pz by 2 pi multiplied by phi multiplied by Ia. Here also Pz by 2 pi is a constant term because poles, conductors, and the bottom is a constant. 2 pi, it's a number, numerical value. This is always constant, multiplied by the flux generated as well as the armature current flowing through the armature winding. So this is, we started with these basic equations, and if you want the derivation for this, you go back to the 8th week discussion where we have discussed how these have generated a clear discussion we have did there by taking a conductor, by applying the force equations, and we developed these equations. It was a thorough discussion we had 2 weeks back. You can refer to the discussion if you want to understand the derivation. And after that, we started looking at a DC shunt motor diagram. We can see here we have the field winding in a shunt position in parallel with armature winding and armature of the motor, inside which we have the armature resistance RA in series with the back EMF EB. So the same kind of supply we are giving, which is the same as armature voltage and also supply voltage. We call it a terminal voltage of the DC motor, which is V. Now getting into the topic is adding an external resistance to our armature. So here the armature resistance is RA. If I want to add an external R external in series with the armature, what changes will happen in a motor? How the speed will change, how the EMF induced will change, how the other parameters will affect. Do they affect or do they not affect? So such discussions we have did, and with that we saw example, a numerical problem where we were provided with the DC shunt motor with a armature resistance of 0.5, and we are added with a 3.5 ohms of resistance in series with the armature winding. In these two cases, for both load and no load condition, we analyzed 4 cases. Our 0.5 armature resistance and no load, 0.5 armature in on load, 4 ohms resistance in no load, 4 ohms resistance in load. For these 4 conditions, we calculated EMF generated and also the speed at which my motor is running. So if we calculate these 4, those are the 4 questions. What is the no load speed after connecting 3.5? What is the on load speed after connecting 3.5? So we did all these calculations, and we arrived at the final question, which is a speed regulation. So this equation, this condition is only for after connecting 3.5. If it is before connecting 3.5, we have to do no load speed minus load speed by no load into 100. But this speeds, all the speeds will be before connecting 3.5. That is at 0.5 resistance condition. Yeah, that also you can do. As an exercise, you can do as a tutorial. You can also do. So basically, this is the concept you have to understand. Whenever you add an external resistance armature, if the field will change or not, if it changes, what how my proportionality constant would be, and if it won't change, we have to take the phi as constant, and also the speed how it is changing. So yeah, so if you have any doubt regarding this, you can ask me now, or if you have any doubts regarding any previous lectures discussion also, you can ask, or if you are having any doubts in the other topics, you can also ask them. We will try to answer, and if not, if you don't remember the question now, you can raise the questions in the discussion forum as well. In your NPTEL portal, you can raise the discussion forum, or you can also mail to us directly as well, our TAs, and yeah, we will definitely get back to you on the question. But please don't hesitate to ask doubts during the session, and also in the discussion forums. Please raise the doubts in the discussion forum. Please try to discuss everything which you have doubts on, because this will ultimately help you in solving the assignment questions. And don't forget to attend the session on the 7 p.m. where you will be discussing some other concepts which I might not cover in this session. So the all concepts which we cover in this tutorial session will eventually help you to solve the assignment questions. So please don't skip the tutorial sessions, the rest of the 2 tutorial sessions which will happen along the week. So today itself you will be having another session around 7 p.m. Please join for 1 hour and discuss, and you can later revise it. So you have any doubts, you can ask me now. Okay. So if you don't have doubts, no problem. You can always raise the query in your discussion forum, and we always free to discuss the questions with you and discuss the solutions with you. So please don't hesitate to ask the questions, and